All right, let's go ahead and get started. So y'all went through section 8.4 with Yana on Friday, right? Any questions on that before we move on? So alternating series stuff, conditional convergence, absolute convergence. Did you talk about the ratio test? Okay, and the root test? Right. Any general questions about any of that stuff? Okay, so we'll get moved past that. If you do have questions that kind of arise in this next section.
Sorry,
Yeah.
when it talks about absolute conversion for the alternating series test.
Yep.
How do you know the absolute value of an alternating series actually converges?
So when you take the absolute value of that series, so I don't know if she went through this example explicitly. I'll just pick one we can talk about. So I'm not sure if y'all went through this one, but so when you're talking about absolute convergence versus conditional convergence, that question really only has meaning for a series, or for a series that has some positive, some negative terms. Alternate series do. So this series alternates, right? So when we're going to talk about its convergence, we can say it's convergent, we can also be more specific about it. So, and you have a lot of freedom in how in what order you choose to attack these. So I'll let you all decide. Do you want to look at this series as written or the absolute value of it? Probably going to have to look at both, but another way to say this, do you want to look for absolute convergence first or conditional convergence? Absolute convergence? Okay. So then I am not going to look at the series as written. Oh, why aren't you working? I'm going to look at this series instead. The sum from 1 to infinity of the absolute value of the thing I gave you. How does the absolute value alter this series? Right, so the -1 to the power of n, that term, basically the only two values that part of this sequence takes is -1 or 1. So taking the absolute value of that basically makes it always equivalent to 1. So in looking at the absolute value of that sequence, the underlying series, we're now looking at the series of 1 over n squared. Do we know anything about the convergence of this thing? The sequence converges to 0. If Yana didn't go through it with you, I will talk about it now. There's a very quick test called the p-series test. And basically what this p-series test is for, it's kind of limited in its, scope, but it's very powerful in the things it's useful for. So if you have a series that looks like this, 1 over n to the p, then what's the condition for convergence? If p is greater than 1, I get convergence. If p is less than or equal to 1, I get divergence. So very clear boundary there. So I think we've talked about, in fact, that boundary line of 1 over n, or when p is equal to 1, we've talked about this series, right? What does that series do?
Divergence.
It diverges. So that's kind of the quintessential example of a sequence that converges to 0. But if you take the series on that sequence, it diverges. So now, having seen this p-series thing, which you are totally welcome to kind of use as evidence for your argument about whether something converges or diverges. As long as your series kind of fits this mold right here. By the P-series test, does 1 over n squared, does that series converge or diverge? Should converge, right? P is bigger than 1. The power on n is strictly larger than 1, so it converges. So I found convergence. Do I know what kind of convergence I have? So 3 options basically. I either have absolute convergence, conditional convergence, or I have to do a little more digging. Why is it absolutely convergent?
Absolute. That's
Basically, yeah. Is it possible for something to absolutely converge and then diverge if we look for conditional convergence? No, it's impossible. So absolute convergence is something stronger. Hopefully the name implies that, but it's something stronger than conditional convergence. So if we look for absolute convergence and we find it, we're finished. Question?
Wait, I'm a little confused how, you say 1 over n diverges, because like if you put bigger numbers or as like n gets bigger, doesn't it just like get closer to 0?
What got closer to
Like,
0?
if you do like 1 over n,
Mhm.
if n, like the denominator, since like the numbers are getting larger, doesn't like the fraction approach to 0?
Right, so here's 2 things we're talking about here. The limit as n goes to infinity of 1 over n. That's 0, right? I totally agree with that, but what's the difference here? What am I actually saying is divergent? The series. So basically the sequence, if I just look at the list of terms in that sequence, yeah, they're gonna get arbitrarily close to 0, but they're not gonna shrink fast enough that if I add all those things together.
Oh,
So if I take the sum of those things, that blows up. That basically those terms don't shrink fast enough for that sum to get away from. Really important distinction, really good question. What if we failed for absolute convergence here? What would we have to do? What could we say about conditional convergence? In fact, do I have an example where I have to go back and forth? So let's do this one here. If I take the absolute value here, how does that change it?
do the series test, maybe the first test. Where
Well, what I'm saying is this, let's just do the same like sequence of steps that we just did. So if I take the absolute value of this, I get 1 over n, right? What does this series do? This diverges. So we do not have, what kind of convergence do we just prove that we don't have? So no absolute convergence. What does that tell us about conditional convergence? Yeah, we haven't. Basically, we know that the really strong condition does, or shouldn't say condition. We know that the really strong convergence doesn't exist, but maybe the weaker one does. So how do we look at the weaker one? How do we look at conditional convergence? A to the n plus 1 over the ratio test, the root test. Oh, so the 3 big tests I think you probably went over was in order: alternating series test, ratio test, root test.
Yeah, the alternating series test.
Yeah. So yeah, we look at the alternating series test. There's a lot of conditions we have to make sure on that thing that it works, right? What are the conditions on the alternating series test?
If the limit of the event or the sequence that doesn't include the alternation.
Okay,
if it
so-
converges to 0.
So I'm gonna back up. So Condition one is, does the thing alternate? It does. All right, so if it alternates, the nice thing about the alternating series test is if it alternates, basically the rest of the test involves the part of the sequence or the series that doesn't alternate, right? So we'll call that B sub n. I think that's what she called it for you. What do I care about B sub n? What do I have to look for?
Each value has to be less than or equal to the value before it,
Okay, so it decreases.
and its limit should go to 0.
Dn goes to 0. Does it decrease?
Yes.
Let's be clear here. When we say B sub n, what is B sub n? It's the non-alternating part. Does it decrease? Does it go to 0? Yes. Therefore, what? So the alternating series converges. So basically, the thing that gives me conditional convergence is the fact that the series as defined converges. But if I take the absolute value of all the terms in the sequence and add those up, that diverges. So it only converges under the condition that I allow it to alternate. If I force all the terms to be positive, I don't get convergence. This is conditional convergence. Like what? I mean, you can always try them.
That test was called what?
This is the alternating series test. Actually, I'll label that down here. So these conditions right here that I've made the boxes for, this is the alternating series test.
So if you get a question on the same test, we go absolute. Conditional.
So it either converges absolutely, converges conditionally, or it diverges. So yeah, there are no sub-classifications of divergence. It's just divergence. We could try the ratio test. How does that one work?
The series
So basically,
n plus 1 over the series.
did she talk much about why the ratio test is a thing that works the way it does? It is the most versatile, but basically, here's what we're trying to do basically with the ratio test. Probably the series we have the best idea of how they behave are geometric series. So what we're doing with the ratio test is we're taking a series that's not geometric, and we're hoping that as n gets really, really big, basically the ratio between like back-to-back terms becomes predictable. So if that ratio exists, then even though you don't have technically speaking, a geometric series, you have a series that you can, if you look far enough downstream on, it starts to mimic the behavior of a geometric series enough that you can make some conclusions about it. So let's see what the ratio test tells us here. I'm looking at absolute values, right? So doesn't this just become this, the limit as n approaches infinity of 1 over n plus 1 over 1 over n? Which if I simplify that becomes the limit as n approaches infinity of n over n plus 1. So absolute value basically just takes those alternating portions. As long as those alternating portions are, just swapping back and forth between -1 and 1, you can replace them with +1. What does n over n plus 1 do as n gets really large? It goes to 1. What does that tell us about what's the ratio test tell us in that case? Nothing. So, yeah, this is one of those cases where the ratio test is not really going to give you anything. I think the alternating series test is probably something you have to do. How are we doing so far? Okay. Anything else about Friday stuff? Okay, so let's move on to 8.5. Yana was right that the ratio test is the most versatile thing going forward. So something I want to talk about today is a power series. So what is a power series? So at its heart, it's no different than the other kinds of series we've talked about, but I do have one characteristic that we're not used to yet. So basically what a power series is something of this form. So every sequence and series we've talked about so far, well, maybe not every, but the majority of them have, what's been the variable, what's been the unknown in those sequences or in those series? N, right? So now I am bringing in X. But something I want to point you to before I kind of go any further is in this notation here, the way I am building up this series, what is the independent variable? Or like, what's the symbol I'm using? What's the variable I'm using to construct this series? What's the thing that actually changes in here? It's still N, right? As far as we're concerned, like in the way this is built, X is like a fixed value. So X is a variable, but we're not really allowing it to vary in the way we construct these. What are C sub N? Basically, C sub N is like a sequence unto itself. It's a list of the coefficients of all these terms in this series. So basically what we're going to do here is, even though X technically is a variable, we're going to treat it like, basically we're going to fix it and figure out where it converges, where it diverges. So basically building up from where we've been to where we're going. Basically, I've given you sequences and we've talked about, all right, just here's the sequence, does it converge, doesn't diverge? And then we kind of made that a little more granular and said, all right, convergence, we can do better than that. We can say, does it absolutely converge or does it conditionally converge? So now with power series, what we can do is we can give intervals of X values for which it converges. So let's look at one. This series right here, I'll tell you right now, sometimes it converges, sometimes it diverges. So let's find those values of X that actually makes it converge. So basically, if we can give the values of X where this thing converges, then we can basically we can talk about where it converges, where it diverges. So probably the first time we've looked at something like this, what's a good way to start? Do we know what this series looks like? So first term is what? 1. And then? I don't think X squared is the second term.
X.
X. Throw a couple more in there. Does that help? Does that give us any kind of insight on what kind of series this is or how it behaves?
less than one.
How come?
Negative.
Why'd you say that?
Because if it's one, you're just gonna be adding one forever, which is like the approach infinity.
Okay.
But if it's less than one, the values you're adding are getting smaller and
All
smaller
right.
over time.
So what you're saying is that you think between -1 and 1, this thing will converge. What other kind of series act that way?
Geometric.
Is this thing geometric? Okay, it should be geometric, right? If it's geometric, then you should be able to tell me what its common ratio is. So basically, as I go from term to term in this sequence, am I multiplying by x each time to get to the next term? Okay, so I have a geometric sequence or series whose common ratio is x. What do I know about geometric series? When do they converge? No one's talking to you. So what do I know about geometric series? Under what conditions do they converge? Right. Yeah, I just realized she heard series. Let's talk. All right. So under these conditions, this thing converges, right? So this right here, I believe the logic, I think that we have some good evidence, some good arguments for the fact that this thing converges between -1 and 1. So x values strictly between that or strictly inside the interval are going to converge. So we talked about, going forward, the ratio test is going to be this very versatile thing. Let's at least make sure that it bears out what we were already claiming. So how do I find the ratio, or what is the ratio test? How does that thing work? When I do the ratio test, am I looking at the sequence or the series? I want to learn about the series, but I'm really looking at the sequence. So I want to know, as n gets really big, what happens to back-to-back terms? Like, what's the ratio between consecutive terms? What does the nth term in this sequence look like? So the nth term should be x to the n, right? What is the n plus 1th term? X to the n plus 1. All right, so let's look at that ratio now. Can I simplify it all? What is x to the n plus 1 over x to the n? Simply x, right? So the absolute value of x. For the ratio test to give me convergence, what do I need that limit to be? Less than 1, right? So basically what I have here is the absolute value of x is less than 1. So this ended up being kind of a simple application of the ratio test. In this limit notation here, what am I looking? I'm looking for n to get really large, right? Where does n show up in this limit? Nowhere now. So really, this limit is simply just absolute value of x is less than 1. So we agree that the absolute value of x is less than 1 is the same as the thing I already boxed in. So basically, x has to be within 1 unit of 0. So basically, this thing here is equivalent to -1 is less than x, which is less than 1. How we doing? Okay. So, and like Yana said, the ratio test is going to be very I'm never gonna promise you always, but when we're looking at things like this for like the convergence of a power series, where a power series converges, that will very typically be your first line of investigation. So, changing things here. So, incorporated this n factorial. I want to know what values of x this thing converges for. Any thoughts so far? Like initial predictions of what this is going to do? What's going to happen to the terms is like as basically as n grows. Should we look at a few? The first term should be. Do we know what 0 factorial is? It's 1. So first term should be 1. And then the second term should be x. So starting off kind of like it did before, right? Then plus 2 factorial x squared. So 2x squared plus 6x cubed plus 24. So those coefficients are going to keep getting very, very large. All right, so have some sort of idea how this thing behaves. What can we do to figure out where it converges? Like what values of x it converges on? So let's try the ratio test, see what that tells us. All right, what do these terms look like? N plus 1 factorial times x to the n plus 1. N factorial x to the n. Does this simplify at all? So we just saw how the x to the n plus 1 over x to the n simplifies. I'll call that absolute value x and pull it out. Do the factorials simplify in any convenient way? How so?
Plus 1 times n factorial.
Okay, so let's write that down and we'll talk about it. Let's talk about why I can write n plus 1 factorial as n plus 1 times n factorial. We okay with that? Let's do a concrete example here. If I write 4 factorial, what does that mean? Basically, it's this descending product. So could I say that 5 factorial is equal to 5 times 4 factorial? So that's basically the logic we're applying here, is that if I want to take the next, basically the next factorial product up, it's going to include the product of the one before it multiplied by n plus 1. So I have that times this other thing, x, or we just said this was x. So when I simplify, what am I left with? Just n plus 1 times x. Times the absolute value of x. One thing I want to point out, so it doesn't look like I'm just cheating. Is it clear why I'm taking the absolute values off of n plus 1? Why am I allowed to do that? Yeah, n starts at 0, so the absolute value is not, there are no negative values there to flip to positive. All right. I want to know where this converges, right? So the ratio test has to be Like, what do I need the ratio test to give me? I need this to be less than 1, right? How could that happen? What's gonna have to be true of this thing?
Needs to be. Right.
What is going to happen to, so basically, I'm taking the limit as what, like. What am I allowing to change in this limit? Just n, right? So really, what's gonna happen to? Maybe be helpful if I just pulled the x out of the limit, since the limit has nothing to do with it. So basically, I need this limit to be less than 1. What values of x are going to allow that to happen? There are some. There's 1.
0?
The only way this converges is that,
I just thought that 0 times infinity, you can't really compute.
but we're not really computing it.
Okay.
So really, here's what's happening here is that if x is anything other than 0, eventually that limit of n plus 1 as n goes to infinity will overwhelm it. It'll be bigger than 1. So the only way this series converges is if the series looks like this. Actually, I'll write like this. Is if it looks like 0 plus 0 plus 0 plus 0, and so on. So if we allow x to be anything other than 0, this thing will eventually, it grows too fast, it'll overwhelm whatever tiny positive value of x you try to use. So for what values of x does this converge? This single one. So it converges under these conditions, but in a very non-interesting way. This is just a constant 0 series. Question?
Are we basically just saying that limit is always going to be infinity, so then we make that bring us to multiply by 0?
Yeah, essentially, yeah. Questions? All right. Let's talk about this thing. All right, what should we do? So what's our kind of go-to tool for these things going to be? Use the ratio test. So the limit as n goes to infinity of, and basically I'm writing the same thing down every time here. Basically, this is what the ratio test is. I want to know what the ratio between consecutive terms looks like as I let n grow very, very large. So in this case, tell me what that ratio is going to look like.
Two x minus 5 to the n plus 1 over n plus 1.
2x minus 5 to the n plus 1 over. So that's my basically my n plus 1 term is this thing here that you just said. And I want to divide that by, yeah, basically the sequence as defined. 2x minus 5 to the n over n. And I would really love to simplify it however I can. Does any simplifying happen? What happens? Okay, so what am I left with after I do that cancellation?
Minus 5 7.
two x minus 5 times n over n plus 1. And I want this thing to be less than 1, right?
Sure, Matt.
Yeah, absolutely. One thing that I think is important to keep in mind here is you're very often going to wind up with a fraction divided by another fraction. It might be useful to rewrite this as, let me do it where I have more room. The limit as n goes to infinity of, how do you divide fractions?
Multiply by the reciprocal.
Multiply by reciprocal, so that's exactly what I'll do. So 2x minus 5 to the n plus 1 over n plus 1 times n over 2x minus 5 to the n. So I can't cancel n over n plus 1 at all. Like nothing in there simplifies. But as far as the 2x minus 5, how did I end up with 2x minus 5 with no exponent on it? Right. So it's also to the first power. And what were the powers of these two things? I took basically they had the same base, 2x minus 5, and I divided that base to the n plus 1, divided by that base to the n. When you divide things of like bases, what do you do with the exponents? Subtract them, right? N plus 1 minus n is 1. So that's why this simplifies the way it does. Can we evaluate this limit? It goes to 1, right? So I end up getting this. The absolute value of 2x minus 5 is less than 1. And I solve for x now. Because basically I want a range of values for x. What does it mean for the absolute value of something to be less than 1? It could mean that this thing is less than 1, right? But it also means that it has to be bigger than -1. Basically, it has to be between those two things, right? So now I have like this 3-branched inequality. Can I simplify things like that? So in algebra, I can basically, the way we kind of think about it in algebra is whatever you do to one side of the equation, you can do to the other side. But now I have these 3 separate branches. You can deal with them all simultaneously. So adding 5 to all 3 of those branches gives me 4, which is less than 2x, which is less than 6. Or 2, which is less than x, which is less than 3.
So we need one and this one.
I didn't ignore it. Where did it go? I took the limit of it. So the limit of that, and totally could have been more clear about this. So let me try to buy back some real estate. I'm going to rewrite this. So I for now, I think it's helpful to basically pull the things out of the limit that the limit is not really going to affect. So I only care about this limit as far as n is affected. So if I pull that x, basically the x expression out, what's that limit there? What is going to happen to n over n plus 1 as n gets really big? It goes to 1. So basically, I didn't ignore it, but it becomes identical to 1. So I kind of canceled it out since it was multiplied by other things. Go ahead. If it went to 2 or 3, then you just basically replace it with whatever it actually converges to. So maybe not today, but we'll see examples that do that. Yeah, but basically, since that limit exists, I replaced it with what its limit was. So now what I have is this: x converges as long as it's between 2 and 3. But here's the thing, what does the ratio test tell us if the limit is exactly 1? Tells you nothing, right? So here's what we've learned. We know that X converges if it's strictly bigger than 2 and less than 3. We don't have a good idea yet what it does at those boundaries. So we have to test those kind of individually. So let's do that now. If X equals 2, what does our series look like? -1?
You want to see the number.
Should be -1 to the n over n, right?
Yeah.
So let's be clear, where did that come from? So going very back to the original definition of this series, and now basically when I fix the value of X, I'm not really looking at a power series anymore because I'm not allowing X to vary. I care about when X equals 2 and only 2. So now I have this series, -1 to the n over n. Do I know what this series does? All we care about is that it converges. Because we know that for that value of X, it'll converge. What about when X is equal to the other boundary, 3? Then what series am I looking at? 1 over n, what does that do? The sequence goes to 0, but that's not really what we're asking about. I don't know what the sum of the terms goes to. So what does the series do? Does it also converge? This is a divergent series. Give me a reason, other than we've seen this exact one before. Right, so you can always basically group up more halves and add those on there. There's a test we talked about earlier today that you could use to justify this.
P-series.
Yeah, the P-series test. The power on n is not bigger than 1. It's exactly 1, so it diverges. So because we know this thing converges at X equals 2, diverges at X equals 3, we can give basically we can update the values of X a little bit. X is equal to 2 or bigger than 2, but it has to be strictly smaller than 3. Questions?
Isn't that a P series?
Yeah, absolutely. I'm gonna put on the next slide because I'm just not interested in it. Any more questions here?
That one's what's this like, it's to the bottom of the.
That's a good question. Yeah, we're playing out. Anything else? Okay, so the P-series thing, before we look at this function. P-series test is a very quick and easy test to do, but it's also kind of limited in the things it works on. So what does the sequence have to look like? So basically, what does the expression in this box have to look like for the P-series test to work? 1 over n to the p. So why can I not use this P-series test on the X equals 2 condition? And it's not just -1. I mean, if it was just -1, no alternation, the P-series test works. Basically, I'll kind of generalize this a little more for you. The P-series test works if you have, I'll call this a C, a constant over n to the p. So the fact that it alternates. So here's the thing, if it was just -1, then what would the series look like? -1, -1/2, -1/3, -1/4. They're all negative, right? So the fact that you have like this series where you're constantly adding things of the same sign means the sum gets away from you, it diverges. It's the alternation that makes this sum convergent. The fact that a lot of the terms are basically eating into the sum. Basically keeping the absolute values close enough to zero that the sum will converge. Is that better? All right. How do we handle this thing here? Was pretty gross, right?
Taking the ratio test again?
Let's try it. Let's see what happens. One thing I want to point out, because it was something popular early on, can we do like a L'Hopital's rule workaround here? What's that?
Can.
I don't think we can either. Why don't you think we can?
It's like the exclamation, I don't think, I forget what it's called.
Factorial?
Yeah, factorial.
What kind of things? A factorial is a very specific function that only works on what kind of numbers? The basically the natural numbers. Non-negative integers. So yeah, I can't make a continuous function out of this. But what I can do is set up the ratio test, and hopefully that simplifies for me in a nice way. I'm going to skip right ahead to just bringing in the reciprocal. All right. Anything jump out at you about what simplification we can use?
Negative 1 to the n, you can cancel that out, and the x to the 2n. Like the top left and bottom right.
I don't think the x to the two ends go away. But one thing I will say is this, I think the alternating terms I can ignore completely. Is that fair?
Yeah.
Why is that fair for me to say that? The absolute value basically makes those alternating negative ones and ones become one. I am also going to basically break apart these exponents wherever I can. What am I missing? No. Is that it? I didn't write them out in totally consistent orders, but I think that's everything. Does anything else simplify in a nice way for us? Okay, is there anything left over when I cancel this? The x squared should be where? So x squared in the numerator. And the 2 squared. All right, can we deal with the factorials? How so?
F plus 1 factorial is F plus 1 times n factorial.
Okay, so I can write both of those as n plus 1 times n factorial, n plus 1 times n factorial. The numerator still has these in it. So the limit is n goes to infinity of what? Absolute value of x squared over 4 times n plus 1 squared. And as always, I want this to be less than 1. Would it be okay if I left this right here? There's more to be done with it, and I don't feel right about trying to squeeze it into a minute. But any last minute questions about how we ended up at the place we ended up so far? Okay, we'll pick this up on Wednesday. Otherwise, I'll see you then.